Hello, am I audible? Um, okay, yes, you're audible. So, good morning, everyone. Welcome to the sixth day of the Deep Learning Summer School organized by IIIT Jabalpur. I hope you all had a refreshing weekend and are ready for another exciting week of learning. I am Supriya Sharma, your session chair for today. It's a great pleasure to welcome back Dr. Shiv Ram Dubey from IIIT Allahabad, and many of you would have remembered the insightful session he delivered earlier. So, with his deep expertise in deep learning and related areas, we are excited to learn from him once again. So, welcome back, sir. And I would now request you to kindly take over and start the session. Thank you, sir.
Okay, so very good morning to all of you, and thank you very much. I hope I am audible and my screen is visible.
Yes, sir, you are audible and your screen is also visible.
Okay, thank you very much for confirming. So, in this particular session, we are going to talk about a type of neural network which is called convolutional neural network. And convolutional neural network is especially built for dealing with the matrix of data, where our data is available in a matrix form. So what kind of data is available in the matrix form? So if we have image, usually image is represented as a channel. So where channels are nothing but kind of a matrix, means these are only numbers. So if you see any image, it has, if it is a color image, it has three channels, red, green, and blue. And the first channel is red, second one is green, third one is blue. And suppose if we say that the image has a resolution of 256 cross 256, for example, it means that we have 256 number of rows and 256 number of columns in that particular image in one channel. Similarly, 256 number of rows, 256 number of columns in second channel, and similarly in third channel. So if we consider a particular coordinate in a spatial, for example, suppose if we say 100, 100, it means that in this matrix, if I go to the location 100, 100 in every channel, then we will get three values. One in the red channel, one is in the green channel, and one is the blue channel. And that is actually called the pixel values of the image at any given coordinate or at any given index. Okay, so what type of problems we can solve with the images? Now, if you see, this is a very broad area of image processing and computer vision where we deal with the images, and plenty of problems nowadays are being solved using images. And for example, if you just see, the face recognition is one of the applications where image need to be dealt with. Any sort of problem where visual information is required to be processed, that's where this image or video comes into the picture. Even if we have video as the input, so video is also nothing but this is a sequence of images. Actually, we say sequence of frames. So suppose if you have a video with 30 frame per second, what does it mean? It means that in 1 second of video, you have 30 images coming in a sequence. And that's how, if we have the sequence of images, then it forms the video. So even if we do the video processing, at the end we are doing actually the image processing, because videos are built with the images. So there are plenty of applications, like we can do image classification. If we are given with some images, there are some objects inside the image, and we want to classify the object which is inside the image. It should get classified in which class. This is one application. Sometimes it is also possible that multiple objects are present in the image. So here we can see in this case we have a cat inside the image. And suppose if someone asks the question that okay, what is the category of the object in this image, then will say cat. Then this is a problem where we want to classify this entire image into cat category. But suppose if in the same picture we have the dog also. There is a cat, there is a dog, there is a human. And then if we ask that what is the category of the objects in the image, then we cannot classify entire image into one of the class, because in that case we do not have a single object in the image, we have multiple objects. Then the problem becomes even little bit complex as compared to image classification. Then there we have to first find out where is the object in the image, and then only consider that portion of that particular object, and then classify only that portion. That is called actually the object detection or object recognition, where first we need to find out where is the object and then we need to do the classification. Similarly, there could be plenty of applications like in agriculture. Someone wants to do the recognition of disease in the fruit. So we have the pictures of the fruit images. Suppose you have the apples or mango, and you want to classify just by looking some damage in the there is some symptoms which are present in the fruit, and from that symptoms, if we want to find out that what sort of disease is there, then also we can perform the classification here. So there is plenty of applications where images can be utilized in the applications. Then now question comes here, if images can be used to solve a lot of problems, then and we all it means that we have to do some processing over the images. And if we have to do some processing over the images, is it possible to use the concept of machine learning or the concept of deep learning to perform this processing of the images? We already have the traditional ways of doing processing of images, that is called image processing. So many of you might have gone through a particular course of digital image processing where there are plenty of manual approaches through which we can do the processing of images for different purposes. For example, someone wants to find out the ages from the image. Someone wants to find out the low frequency information from the image. Someone wants to find out high frequency from the image. Someone wants to perform the segmentation of the object from the image. Someone wants to perform the segmentation of face from the image. So plenty of such image processing, traditional image processing approaches are there. But because in this course we are focusing over the data-driven approaches. What we are focusing is the machine learning or deep learning based approaches. And then question comes here, can we utilize machine learning or deep learning approach? Is specifically can we utilize the neural network to process the image? That is one of the important questions. But now if you see the characteristic of the neural network, so what is the characteristic of the neural network? If you see, a neural network requires some input, we have some hidden layers, we have the output layer. But the input which is required by the neural network, that input requires the data in the form of a vector. Why in the form of a vector? Because because if we have a sample, and if that sample is represented, if that sample is represented in a feature form or in the form of a vector, then we can provide it as the input, like this input layer. In this picture we can see here. So for example, in this picture, what is the dimensionality of the input data? The dimensionality is 3, because we can see these 3 feature points are there. These 3 different dimensions are there in the input. But the input need to be in a vectorized form. If input is there in a vectorized form, either it is having single value, or its dimensionality is 2, or its dimensionality is 10 or 100 or 1000, whatever. But it should be in a vector form. If it is in a vector form, then we can give that sample as the input to our neural network. Okay, so now let's come to our image again. Now we have the image, and what we want to do, Now we want to give this image as the input to neural network. But what we have just seen, neural network can receive the input in the form of a vector. But what is my input? My input is not vector. My input is a matrix. So how we can give this matrix as the input to the neural network? So if you see in a very straight way, it's not possible. It's not possible to give matrix as the input to neural network because neural network is designed in such a way that it requires the vector as the input, vectorized input. Then what we can do? We can then how to provide this image as the input to this neural network. So a simple approach that can be followed is, can we convert image itself in a vector form? So how we can convert image into a vector form? There are two different ways. One way of converting image into a vector form is just take the image and just stretch it. Just stretch it to make it a single vector. What is meaning of that? Suppose we have the first row of the image, take the second row of the image and append in the first row itself. It means that now first row it will become large, means suppose earlier if we had d number of values in the first row, so after having the second row also appended in the first row, now it will become 2d. Similarly, take all the rows and append it in the first row itself. Then what will happen? So if suppose if the dimensionality of my if the spatial resolution of my image was 256 number of rows and 256 number of columns, then it will become a single vector having how many number of values? 256 into 256, a single vector it will become. But though we can perform this particular approach, we can use this particular approach, but what is the problem? One major problem with this approach is this input layer, its dimensionality will increase drastically. Why it will increase drastically? Now, if you see 250, suppose if my spatial resolution is 256 cross 256, then the number of input that we get in input layer itself will be 256 into 256, which is going to be huge. And if we have 256 into 256 number of inputs in my input layer dimensionality, then in my first hidden layer, we should have at least that many number of neurons. Usually we should have more than that. So if we have more than that number of neurons, just if we take a lump sum number, suppose if the dimensionality of my input layer is 10,000, just for example, and suppose the number of hidden neuron in the first hidden layer is 20,000. Okay, it means that every neuron in my first hidden layer will receive 10,000 inputs. It means that every neuron in my hidden layer will also have 10,000 number of parameters. And if we have 10,000 number of inputs and 10,000 number of parameters, and this we have to repeat for 20,000 number of neurons in my first hidden layer. And for every hidden layer, we need to perform W transpose X plus B. Then now we can assume how many number of dot products we might be doing. So we are doing 20,000 number of dot product, and the dimensionality of each dot product is 10,000. It means 10,000 number of multiplication plus 10,000 number of addition we are performing with one neuron in the hidden layer. It means 20,000 number of computations we are doing with one neuron, and we have 20,000 such neurons. So how many number of computations we are doing? 20,000 into 20,000. So now you can assume what will be the cost, what will be the computational cost of this particular approach if my input layer, if the dimensionality of my input layer is very large, and that is going to become a bottleneck here. And it means that if we use this particular approach, that if we have an image and just simply stretch it and convert into a column vector and give as the input, that is not going to be worth in terms of computational complexity, because the number of computation will increase drastically. So this is not a good approach. This is one sense. In another sense also, this is not a good approach. What happens here, even as a human being, for example, as a human being, we are able to see that in this image, there is a cat. On what basis we are able to judge that there is a cat here? Because when we see its 2D layout, when we see the relationship of the pixel values with its neighborhood in all the directions, then it forms a pattern. And that visual pattern mimics how cat looks like. And that's what our mind is able to interpret. Because there is a 2D relationship among the neighboring pixel values, which forms a pattern, and that pattern we are able to interpret. What will happen if I just stretch this image into a single column vector and give it to you? And if I ask you, can you identify what sort of object is there inside this image, which is now stretched? Then for us it is extremely difficult problem, and we will not be able to find out what is the object there because we do not have 2D relationship. That is lost. Once we have stretched, 2D information is lost, 2D relationship is lost. And and 2D relationship is one of the important factor in the image to recognize what sort of object we have in the image. So this approach is going to be problematic in two terms. One, we are losing the 2D relationship, which is not good for recognition purpose, and we are increasing the dimensionality of my input layer drastically, which is not good from the computation perspective. So it means overall this is not a good approach. Okay. Someone can do some different ways of converting this image into a vector. For example, someone can say that, okay, why not to use some traditional feature extraction technique? Let's extract some feature and then use that feature as the input, and that feature is usually low dimensional. For example, suppose someone wants to extract the local binary pattern. Local binary pattern is one of the traditional approach to extract the features which actually encode the 2D relationship locally. And if we do that, then image is actually represented into a 128 dimensional feature vector. Then we will give that 128 dimensional feature vector, that vector as the input, and we can train the neural network. That's okay. So this approach looks fine, better than stretching into single column vector, but still there is a major drawback. What is the major drawback in this approach now? That if my feature extraction technique like local binary pattern, if that feature extraction technique itself is not able to encode the required feature from my input image for solving the particular problem, then my neural network is useless. It means that, for example, suppose we want to classify this image into the cat paw part, but local binary pattern, the feature that it gives, the how cat looks like, that information itself is missing in that feature. If that information is missing in that feature, then neural network cannot get that particular idea how this cat will look like, because ultimately neural network is not seeing the cat picture. What neural network seeing is the derived feature, and the characteristic of the cat is missing in that derived feature. Then using this neural network is useless. And actually this was the approach before deep learning came. This was the common approach that people were following. What people were doing usually in early days, the image from image, we were extracting the features. How we were extracting the features, that was dependent upon the what problem we are solving, and for that problem what feature might be important. And that was basically the manual expertise which was being exploited. And for example, suppose someone wants to do the classification based on the shape, then shape-based feature we can extract. If someone wants to look over the texture, then texture-based features we can extract. If suppose for some problem color is important thing, then color feature want to extract. But what is important to solve a particular problem? Earlier, it was being judged manually and accordingly feature was being extracted. So, and in that case also what happens? Some broad feature characteristics are there that manually we can observe and extract. There could be some minute features which we cannot observe as a human being, and it is very difficult for us to extract such features. So this is one of the major problem, even if we extract some manual feature and then give as an input to the neural network. So it means that now we had the image, which is in a matrix form. We have a neural network which can take vector as the input. So both are not compatible with each other. We cannot give that image directly as the input to this neural network. Then there is two ways to fix this problem. One way is to convert image itself such that it can meet the criteria, meet the input requirement of the neural network, and that we find this is not a good way. Then what else can be done? Now let's not change the image. Let's have image as it is in a matrix form. Can we modify the neural network itself such that it can directly take image as the input? So it means that instead of modifying image, can we modify now the structure of the neural network itself? And that's what actually called the convolutional neural network. So now what we will do? Now we will modify this neural network with convolution layers such that it will be suitable to directly deal with the images without converting that into a vector form. It means it can directly work with the matrix. Okay, so before knowing to the convolutional neural network, and we have also seen one computational problem with the neural network. And this convolutional neural network also solves that computational problem. And how this convolutional neural network, which is also referred as CNN or ConvNet or DCN, how this convolutional neural network is able to deal with that computational problem, that actually that is due to two important property of the convolutional neural network, which is called the local connectivity and weight sharing. So what is meaning of that? So now we will try to understand what is meaning of this local connectivity and weight sharing, and later on we will see that why this is important with respect to the convolutional neural network. So let's come to that. So what is global connectivity? Now, if you see, we have seen this neural network, right? This is hidden layer 1, this is hidden layer 2. Now, if you see, any neuron of hidden layer 2 receives the input from all the neurons of hidden layer 1. That is called the global connectivity. This is the global connectivity. And what we are going to do in convolutional neural network, we will basically exploit the local connectivity. Now let's see what is the difference between global connectivity and local connectivity. So in global connectivity, any hidden layer, so if you see this top one is the hidden layer, bottom one is the input layer. Any neuron in the hidden layer will receive the input from all the neurons of its input layer. That is the global connectivity. But in local connectivity, any neuron in the hidden layer will receive the inputs only from few neurons of its input layer. How many neurons? Now, because we are saying only few neurons, not all the neurons. So now this is one of the choice that is available to us that we have to decide. So now we are saying that few neurons, but how many? That is our choice. Suppose someone says that, okay, now I am going to receive the inputs only from 3 neurons. Now that's what we can see in this particular diagram. But someone can say 5 neurons, someone can say 7 neurons, like that. If we say that we are going to receive the inputs only from 3 neurons, that is called the proximity. That is local proximity of this particular neuron. And that local proximity is 3 here. It means that if we take 3 neurons, then what will happen? It will reduce the number of parameters also, and it will reduce the computation also. Here we can see, in case of the global connectivity, in this example itself, in case of the global connectivity, how many number of neurons are there? The neurons is dependent upon how many number of connections we have. So 1, 2, 3, 4, 5, 6, 7. We have 7 number of neurons in input layer. So every neuron in the hidden layer receives the 7 inputs. So 7 parameters are also there, and one bias is also there. So 8 parameters with every neuron, and we have 3 neurons in the hidden layer. So 24 number of parameters are there in global connectivity. However, if you want to find out how many number of parameters we have in the local connectivity, so every neuron in the hidden layer receives only 3 inputs. So it will have only 3 parameters. So 3 parameters and one bias, so 4 parameters. And how many such neurons we have? 3 neurons, so 4 into 3. So we have only 12 parameters. So global connectivity have 21 parameters. This is excluding bias. If you include bias, then it is 24 parameter. Local connectivity has 9 parameters, that is excluding bias. But if we include bias, then it will have 12 parameters. So we can see the number of parameters is reduced. Number of computation is reduced or not. So in case of the global connectivity, when we had 7 inputs, there was 7 weight parameters. then dot product requires 7 multiplication and 7 addition. However, in this case, only 3 inputs, it means 3 parameters, so dot products requires only 3 multiplication and 3 addition. So it means number of computation is also reduced in case of the local connectivity. And convolutional neural network will exploit this local connectivity. Okay. Another important characteristic of the convolutional neural network is weight sharing concept. So now we have just seen the local connectivity, but this is the local connectivity without weight sharing. What is meaning of without weight sharing? Suppose in my hidden layer, if I have three inputs, if my hidden layer, if I have three neurons, and if the first neuron receives three inputs, then their weights W1, W2, W3, these weights are different. And for the second neuron, the weights W4, W5, W6, these weights are different. For the third neuron, the weights W7, W8, W9, these weights are different. That is without weight sharing. If we are performing the local connectivity without weight sharing, number of parameters is increased. Okay, number of parameter is more. But if we have the weight sharing concept, in weight sharing concept, what happens at for any hidden layer, the weights will be same for all of its neurons. So for example, for the first neuron, if my parameters are W1, W2, W3, then for second neuron also the parameters will be W1, W2, W3. For third neuron also the parameters will be W1, W2, W3. What is the advantage? There is no advantage in computation. Computation remains same here because at the end we are going to do multiplication and addition, same number of multiplication addition. But where is the advantage? Number of parameters is decreased. If number of parameters is decreased, then what is the advantage? The advantage will be in the updates because using gradient descent, we have to update the parameters. If we have more parameters, more updates are required. If we have less parameters, less updates are required. And also if you have more parameters, more space is required to save that. And if you have less parameter, less space is required to save that. It means if you have less parameter, then model will become lightweight. If you have more parameter, model will become heavyweight. So that's what is the advantage. Ideally, what we want? Ideally, we want any model which is very lightweight and gives very good accuracy, very good performance. That's what is the overall objective. But if we have very lightweight, then getting very good accuracy will become difficult, challenging task. So that's where somewhere we need to make a good trade-off between the lightweight and the performance. Okay, but this is the concept which is going to be exploited by the convolutional neural network. And here we can see only there was 9 neurons without weight sharing, but only 3 neurons with weight sharing. And if we apply both the concept, means weight sharing also and local connectivity also. Without weight sharing, without local connectivity, the number of neuron was 21, but with weight sharing and with local connectivity, the number of neurons has become 3. Now you can see there is a huge difference. First 21 neurons, now only 3 neurons. There is a huge difference. The number of neurons has been decreased drastically by exploiting these two concepts with the convolutional neural network. Okay. So now coming to the convolutional neural network will have different layers. And a very important layer in convolutional neural network is the convolution layer itself. And the first layer itself is going to be the convolution layer. Because the convolution layer is designed in such a way that we will see shortly, which can directly work on the matrix that we will see. So the first layer is convolution layer. And obviously, we have already seen in case of the neural network that non-linearity layer or activation function is very, very important. Because if we do not have activation function, then our model is useless because it cannot learn any nonlinear projection. If we have non-linearity layer, then only it can learn the nonlinear projection. So activation function is very, very important. So here in this particular example, we can see ReLU activation function, though we can have any other activation function as well. Another important aspect with the convolutional neural network, because we are dealing with the images and with the original this resolution in the matrix form, and at the end, what is the last layer output? Suppose if I'm going to classify into 10 classes, the last layer should have output as 10 class scores that we have already seen in neural network as well. So even in convolutional neural network also, the last layer is always going to be a fully connected layer or a dense layer, very similar to what we have seen in neural network. And suppose if it is a classification problem and you want to classify in 100 class, then last layer will have 100 neurons and it will basically produce 100 class scores. Okay, so then it is very important that this whatever is the resolution of the image in the feature, slowly that resolution should get decreased, and at the end it should become just 1 cross 1, and the number of channel is going to be increased, and then again it will decrease such that at the end it should get converged to the number of classes. How many number of classes we have, that many number of classes scores need to be computed. So that's where another layer also comes into the picture in convolutional neural network, which is called the pooling layer. And the job of this pooling layer usually is to decrease the spatial resolution of the intermediate features that we have. Okay, so these are the different layers. Input layer. So input layer is the image itself here. And we also have a convolutional layer that we are going to see. Non-linearity layer means activation functions. We will also have a quick look on that. Pooling layer, we will also have a quick look on that. Fully connected layer, we have already seen. Last layer is dependent upon the problem we are solving. Suppose if it is a classification problem, then that is the softmax, which is sitting on top of the class scores. So that is going to be the classification layer here. So these are the layers which is to be used to build coordinates. On top of that, we can have some regularization layers also. For example, we can have batch normalization, we can have dropout, or we can have any other form of regularization layers. Okay, so now let's go one by one. Input layer need not to discuss because our input is the image itself. Image is the input directly image in a matrix form without any modification. When I'm saying without any modification, that excludes the data augmentation. Data augmentation is allowed. That is, there we are not changing the form of the data. Form of the data remains same as the matrix, even if we apply the data augmentation. Okay, so input is my image. What is the next layer is the convolution layer. So now we have to talk about what is the convolution layer and how this convolution layer will work. Okay, so now the first layer itself is going to be the convolution layer. So now let's assume that I have an image, and suppose this image comes from Cipher dataset, CIFAR, Cipher 10 or Cipher 100. This is one of the widely adopted dataset for image classification problem, and they are small in resolution. So usually it is efficient to deal with. So their dimension is 32 cross 32 cross 3. It means that now we take an image. Let's assume this image comes from Cipher 10 dataset. And if we get this image, then what is the spatial resolution of this image? Spatial resolution means what? The height and width. So what is the spatial resolution? Height and width. That is 32 cross 32. And what is the depth of the image? Depth means how many number of channels we have. So the number of channel we have here 3, because this is the input itself, which has red, green, and blue, because this is the color image. So it has 3 channel. So this is basically my input image. Okay. When I'm going to utilize the convolution layer, one of the important aspect is we need to preserve the spatial structure. What is meaning of preserving the spatial structure? Means suppose in the image, if there is a face somewhere, then face related features need to be derived in the similar, means in its local proximity, in its similar coordinate, same coordinate. It should not happen that your face is there at this right and up corner, but after getting the output feature of this convolution layer, its feature is going to come to the left and this bottom corner. That should not happen. If it is at the right and top corner, then that particular feature should be there at the particular same coordinate. Okay, then what is this convolution? So now if you are familiar with the image processing, then in image processing, convolution is one of the operation where we have a kernel, right? We have a filter. That filter has the kernels, and if we use that filter and slide over this entire image and take the dot product, then it gives us the output. And that dot product we compute at every location of this input. If we compute at every location of this input that dot product, that for every location of my input, I will get one output. Okay, if you're not getting this point, don't worry. We will try to understand this using example. Suppose my filter here has the size 5 cross 5. What will be the size of the filter? This is our choice. We can decide. We can decide my filter dimension. My filter spatial resolution is either 3 cross 3 or 5 cross 5 or 7 cross 7 or 11 cross 11 or 9 cross 9. Or sometimes it is also possible we can have 4 cross 4. But having 4 cross 4 is not a good idea. Why it's not a good idea? So what happens whenever we consider a matrix of size having odd length, then it is always symmetric with respect to its center. Suppose if we have a 3 cross 3 matrix, then it is symmetric with respect to center. Even if it is a 5 cross 5, it is symmetric with respect to its center. But suppose if someone has a filter of a dimension of its spatial resolution 4 cross 4, then this is not symmetric with respect to center, because center means always a pixel. Which pixel is at the center? So that's where whenever we see in a convolution layer, mostly we find the filters used has the dimensionality always as the odd length. Okay. Now let's consider, for example, the dimensional means the spatial resolution of my filter here is 5 cross 5. It could be 3 cross 3 also. It can be 7 cross 7 also. That doesn't matter so far. It matters, but right now it is not the concern point for us. Okay. Another important aspect in my filter is what should be the depth of the filter? Means how many number of channels will be there in the filter, or how many number of kernels will be there in the filter. And that will be dependent upon how many number of channels we had in my input. So here we can see in my input we had 3 channels. The depth of my input was 3. So always my filter will have exactly same number of channels that we had in my input. If we are doing the normal convolution, suppose if someone is doing channel wise convolution, then case is different. That is a different type of convolution itself. But the vanilla convolution or usual convolution that we perform, there the number of channel in the filter is exactly same as the number of channel in my input. Okay, so it means that here we have these 3 channels. But what is there inside this filter? That is very important thing. What is meaning of this filter and what is there inside this filter? So actually inside this filter, suppose if my filter dimensionality is 5 cross 5 cross 3, it means that I have a matrix of dimensionality 5 cross 5. It means I have 25 values there, and that 25 values, we have 3 such channels. It means we have 75 number of values. Total number of values in this filter is 75. But what are those values? Actually, these values are nothing. These are parameters. So where are the parameters in convolution layer? Whatever is there inside the filter is actually the parameter. Where was the parameter in case of the neural network? The connections that we have, for every connection in the neural network, we had the parameter. Where is the parameter in convolution layer? If I have a filter of 5 cross 5 cross 3, then I have 75 parameters plus one bias term also I can have. And every filter can have a bias term. Then if I ask that how many number of parameters is there in this particular filter, then we can say there is 75 parameters plus one bias. It means total 76 number of parameters we have. Suppose if this filter dimension was 3 cross 3 cross 3, then how many number of parameters we would have in this particular filter? 27 number of parameters plus one bias, or 28 number of parameters total. Okay. Initially, these parameters will be random values, and using this gradient descent approach, we will update these parameters. That's what is the learning process. That's what will be the training process of the convolutional neural network. Okay, so now what we have understood, we have the image, we have the filter. This filter number of channel in the filter is same as the number of channel in my input image. And we also understood that inside these filters, we have the parameters. But now what this filter will do, how we will use this filter with my input image, that's what is the next thing. Then what we will do, now we will take this filter and then we will overlap, or in another word, we can see we are going to just we are going to collide with this image. And suppose if I take the left and topmost corner, and there I am going to keep this filter like this. Suppose I have kept this filter at the top and right left corner, for example. If I have kept it there, then what will happen? Because the size of my image is larger than the size of my filter, but number of channel is same, then what will happen? Now, once we have overlapped this filter with the left and top corner, then it is going to cover exactly same area from my input image. Okay, then what we will do? And in my input image, we will have the values there. We will have pixel values. And in the filter, we have the parameter values. So what we will do now? Now we will perform this dot product between the same area which is covered by my filter from the input image and whatever is the values that we have in the filter. And if we perform that dot product, then that dot product will give us a single value as the output. And that single value is the output in my output image, now in my output channel, at which location, that is governed by where was the center of my filter. If my center of my filter, if it was at a 2,2, so this output will go in 2,2 location in my output channel. Okay, when I'm going to do the dot product here, then how many number of values I'm going to do multiplication? 75 values I will take from the image and 75 values I have from my parameters. So it is actually kind of a dot product between 75 values from image and 75 parameters. So 75 into 75, and that many number of addition will also come. After performing this dot product, we will get this single value as the output at the same location where is my center of this filter right now. And once I have got this value, then what I will do? I will repeat the same process by keeping my filter at every location of my input image one by one. Right now, suppose if it is right now it is at a 2,2. Now I will shift it to 2,3. Then I will then again repeat the same process. Then again I will get one value as the output, which is going to be in the output channel. So if I'm going to repeat like this, here you can see another visualization. So whatever we are saying in the middle here, this is actually, we can just think like this is my filter here. And this filter I'm going to keep at the left and top corner and perform the dot product that will give a single value. Then just slide by one position in the right direction, again repeat the process. Again slide by one position, again repeat the process. And like that, then come to the next row, then again go to all hello. Is there any issue?
No, sir, you are audible now.
Okay, actually I was muted.
Yes, I don't know what's the issue. Sorry.
Okay, fine. So what will happen if I'm going to repeat this for every location of my input image, then for every location of my input image, I will get one output. And if I just keep that in the same order, then that will actually form again another matrix as the output. And that is going to be my activation map, or we can say our feature map, output feature map by using this filter. It means if I have one filter, then one filter will generate how many number of output channel? One filter will generate one number of output channel. But in image processing, if you see, if you have a filter, and suppose if the task of that filter is to extract the horizontal line, for example, then what will happen? That filter will only extract the horizontal line. The rest of the things will be discarded from the image. So, and suppose if you have a filter which wants to detect the corner. So wherever is a corner in the input image, you will get higher response in the output. Higher response means towards 1, otherwise towards 0 in the output. And for other locations where corners are not there, you will get 0 response or near 0 response in the output. So what happens here? If we have a filter can extract one type of information, one type of feature it can extract. Like it can extract the horizontal edge, vertical edge, or diagonal edge, or some small corners, or some oriented edge. So these very small, very basic features we can extract from the filter. But one filter can extract one type of information right now because it is applied directly on the image. So this is very generic features. Then what happens? So having only one filter will not work. Why? Because the one output channel that we have got, it has a very specific information. For example, it has only information about the horizontal edge or vertical edge or oriented edge, or maybe some corners or like that. So then actually it is not going to be work. So what we need to do, we need to extract different type of information from my input image, and which is going to be exploited later on to build some higher level features. So that's where we want, it means that we cannot rely only on one filter. Then what we need to do, we need to extract even different type of information as well. So how we can extract different type of information? We need to make use of more filters. So that's where what happens. Suppose if I take one more filter, suppose this is another filter, and if I repeat the same process, then I will get another channel as the output. Then what is the difference in first filter and second filter? Their parameters are different. Their parameters are different. They are differently initialized. They will be updated differently. So their parameters are different. So they will work differently. So now like that, we got the second one. Similarly, suppose if someone gets one more filter, then we will get one more channel in the output. Suppose if someone gets 96 filters, for example, then we will get 96 channels in the output. And what happens here? Because we were overlapping this 5 cross 5 and we wanted this overlap to be completely overlapped like this, then the center pixel, the center of this center of my filter was started from the coordinate 2 comma 2. Even we cannot keep it at the coordinate 1 comma 1 or 0 comma 0, because then we will not get sufficient value from my input image to perform the multiplication. Because we started from 2 comma 2, it means that our filter will be always kept in such a way that two rows from the left, two columns from the left, two columns from the right, and two rows from the top and two rows from the bottom. For those rows and columns, we will not be able to get its response value because we will not have the enough value in my input image for this dot product. So that's why you can see here what is the spatial resolution of the output channel. It is mentioned at 28 cross 28. Initially, what was the spatial resolution of my input image? 32 cross 32. Now it is reduced by 4. Why it is reduced by 4? 2 from top, 2 from bottom. So the number of rows is reduced by 4. 2 from left, 2 from right. So number of columns is also reduced by 4. So after applying this 96 filters on my input image, what is the output? What is the dimension of my output feature map? Is 28 cross 28 cross 96, where 28 cross 28 is the spatial resolution in terms of height and width, and 96 is the depth of that feature map or activation map, which is actually the number of channels in my output. Okay. Now, how many number of parameters we have in this convolution layer? Suppose this is one of the convolution layer where my filter size, filter dimension is 5 cross 5 cross 3, and I have 96 filters. Then how many number of parameters are there in this particular convolution layer? How to compute? Very easy. Compute the number of parameters for one filter and then multiply that with the number of filters. So for one filter, number of parameter is 75 plus one bias 76. So 76 into 96 is going to be the total number of parameters in this particular convolution layer. Okay. So what is the significance of these filters? As we have already seen, these filters are going to extract the features. What is meaning of that? Suppose if I have this one as the image and I have a filter here. So this is one of the filter. And if I'm going to apply this filter on this entire image, means if I'm going to slide it over the entire image, then it will give me a feature map. What is meaning of this feature map? So here we can see what this feature map is trying to do. So this feature map is trying to give me The white output means the output which is around white, means that is having the larger value, that is related to some oriented edge. What is why? Because this filter itself was giving me the this oriented like diagonal edge. That information is going to be extracted. So wherever we get the oriented edge, there we will get output towards the white color. Wherever oriented edge is not present, we will get the output as the black color. Means it is going to be towards the black side. Okay. Similarly, suppose if someone takes a different filter. Now this is also a filter. This is also oriented is, but now this is in some different direction. Then we will get that particular feature in some. I mean, this is also the oriented is, but that is in a different direction. So in that direction, wherever we have the oriented is, there we will get the higher response. So that's what is the meaning of this filter. So here we can see this is the bank of K filters. For example, if we have K number of filters and all these filters we can visualize and we can see they are actually extracting the different type of information from the image. But then question comes, what type of information my convolution filters will extract? That we don't know in prior, because the values of my convolution filters are initialized randomly. So after training itself, we can visualize and then we can say something what type of information it has extracted. In prior, when if we have not done the training, we cannot say anything about that because all the values of my filter is random, so it is extracting the random feature. So then question comes, if it is extracting the random feature, then how it is going to work? Initially, it is extracting the random feature that will incur huge loss. And due to that loss, I am going to I'm going to update the parameters of my kernel. And that update will give the guarantee that loss will decrease because that update is based on the gradient descent concept. And if loss is only going to decrease if relevant features are going to be extracted and we are going to have the high probability for the correct class, then only loss is going to be decreased. And high probability for the correct class we will only get if my filter is being updated in the right direction, we are extracting the right feature for that particular problem. So after training, slowly my filters will get modified in such a way that it will extract the problem relevant features from input image. Okay, so this is just one example to show that how this convolution is happening. So here we can see we have an image. So image has three channels. The top one is red, this is green, this is blue. And in this case, we have performed the zero padding. So this padding is a different concept. I will come to that right now. Just skip that. Suppose this is my input image. We have red, green, and blue. And I have my filter. And filter, suppose my filter is 3 cross 3, and I have I have three channels in my filter. And total, I have two filters. So this is filter 1, this is filter 2. So if I apply filter 1 here, then I'm going to overlap with the top and left corner of the same resolution. So if my filter dimension is 3 cross 3, I will take 3 cross 3 area from here and then I will perform the dot product. What is meaning of dot product? This 0 multiplied with -1 plus 0 multiplied with 0 plus 0 multiplied with -1 plus this 0 multiplied with 1 plus 0 multiplied with -1, 0 multiplied with 1 means this entire box here in the blue will get dot product with the red one here. And plus for the green channel also, for the blue channel also, everything is going to be combined. And at the end, bias is also going to be added because at the end we have W transpose X plus B. And this W will consist of all these three channels. So multiply our dot product with all these three channels and then plus bias. If we perform this, then output will come to -3. And that's what we will see in the output channel. So output channel, we will have this top one as -3. This is the output of performing this convolution. Next, suppose I have shifted it. Okay, in shifting also there is a concept of stride. Means shifting we can do by any number of position. By default, shifting is by one position, then we say stride is 1. But in this case, we are showing stride as 2 because the shifting of this blue box here is done by 2 positions. So here the stride is 2. And if a stride is more than 1, then spatial resolution will decrease drastically in the output channel. If a stride is 1, then spatial resolution will remain roughly same whatever we have for the input image. And if sufficient padding is done, then this is exactly same. Okay. So now if you see in the previous one and in the previous one, we got output as -3. In the next one, my input is just getting changed to the next window, but my parameters remain same. And that's what was the concept of weight sharing. Now we are having exactly same weights of the parameters, but now applied at a different part of my image. And if I repeat this process, then my output is -1 now. Similarly, again repeat the same process, shift by again two position. If I again shift by two position, now perform the dot product, then I got 0 here. Similarly, if I shift two position now in the bottom side, then means the downside, and again repeat the same process, then I will get the next row of this output, -1, -8, 2. Again, if I shift by two position downside and then shift in the horizontal ways, then I will get the output 303. Instead of taking this first filter, if I take second filter, which is W1, 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 then I will get this second output here, which is 142 -145 313. And again, in that case also, I will simply perform this sliding over this entire image horizontally and vertically. So that's how basically we will be able to get this output channel here. Okay, so before now moving forward, in case there are some questions, let's take those questions, then we will move forward. Okay, so there is a question here. Uh, will we take row-wise values or column-wise layers while stretching the pixels? Anything can be taken, it's up to you. Could you explain the parameter part again? So parameter is there in this convolution of these filters that we have. Suppose if my filter size is 3 cross 3 cross 3, then I have 27 parameter. If my filter size is 3 cross 3 cross 10, then I have 9 into 10. 90 plus 1 bias, 91 parameter. 90 parameters plus 1 bias. So that's how we will have the parameters here. There is another question, why not 3 biases are there, one for each channel, and it was before one for each neuron. That is not the by default concept, but if you want to have the modifications, you can have your own version of the channel wise convolution where you can propose to have the bias for every channel. There is another question, how we decide the filter. So yeah, there is a lot of tricks that we have to exploit so that you will understand once you will do some practice of applying the convolutional neural network. So usually that depends upon what is the complexity of the problem that we are solving. Based on that, we have to decide how many number of filters we should have in each layer and how many number of layers we should have. That is basically some manual things that we need to take care. So from where did this 96 came? This 96 is just one number. Someone can have 128, someone can have 256, someone can have 200, but there are pros and cons. If you have very less, suppose someone has only 10, then that is not going to be good for a complex problem. Why this is not going to be good for a complex problem? Because 10 number of filters cannot extract the variations in the features. Means the different type of features cannot be extracted. If you have more than different type of features can be extracted. But if you have too many, suppose someone wants to say that I have 1,000 number of filters in my first layer, that is also not good. Why it is not good? Complexity will increase drastically. And whatever is the basic features we have, even we might not have 1,000 different number of basic features to be extracted. Fine. So even someone takes 128 or 256, that might be sufficient. This is one problem. Another problem, another important thing is whenever we consider any choices like this, then we try to have that as a power of 2. For example, 128, 64, 256, 512, 1024. Right? Then this is going to be better because if you see your computer is either 32-bit computer or 64-bit computer. So most of the time what happens, because your computer means how many number of bits you have in the computer is always 2 to the power. And if you also have the 2 to the power, like your batch size is 2 to the power, or everything that you are picking as a 2 to the power, then it will better utilize your resources of the computer. So due to that reason, many of the things that we pick in the deep learning is most of the time it is power of 2. So for example, I can have 64 number of channels in first layer, 128 number of channels in the second layer. So like that I can have. Okay. Another question is when we go for medical images, whether it will comes under 2D or 3D images. That depends upon what is your input. If your input has only 3 channels like color images, then that is 2D image. But if you are getting the slices of the images, then that will become 3D image. There you will get the third dimension also. If you see what we are seeing right now, this is not the 3D image. This is 2D image. This is 2D image. Means, and how we are deciding the dimensions which are varying, the dimensions which are varying are the only dimensions that we consider. For example, if I have an image, number of channel is fixed. What we can vary is only the length, this width and height. So this is not a 3D image. If the image dimension is 32 cross 32 cross 3, this is not a 3D image. This is a 2D image. The only number of channel is 3 in this 2D image. And also if you see your filter is getting slided in only 2 direction. This column wise and height wise. That's why this is basically the 2D convolution. This convolution is not 3D convolution. This is 2D convolution because we are sliding it only in 2 dimension. The other dimension is fixed, and that is actually the number of channels in. Okay. Another question is, although it was mentioned that convolution layer maintains the spatial constraints, then on the filter operation, why does it get reduced by 2 columns? Okay, it got reduced by 2 columns because if I am going to apply my filter at the this location 0, 0, then what will happen? Top 2 column and top 2 rows and left 2 columns of my filter will be out of the bound. It will not be overlapped with my image. Then I cannot do the dot product there. So that's why it is decreased by 2. But that can be fixed by having the padding that we will see shortly. So don't worry about that. How to decide a padding, that we will come to that. Is there any calculation that we have already discussed? How to handle the medical images because of image size is high in CT or MRI? We will handle in a similar way. That's what we are doing. That's what we are discussing here. The only thing we can do there to make it efficient is to decrease the spatial resolution of the filters. Okay. So now let's move forward. Now, if you see this convolution layer, it's not compulsory that convolution layer is only at the first layer. Even convolution layer can be repeated, and even we can have the convolution layer somewhere in the middle also. And in fact, in convolution neural network, many convolution layers are being used at different these stages. Suppose we have applied the first convolution layer on this input, and we got the feature map, our activation map of dimension 28 cross 28 cross 96. Even on this activation map also, we can have another convolution. For example, like this. And when I'm going to have the another convolution layer here, and suppose that convolution layer also has its spatial resolution as 5 cross 5. Many times what happens here, you are only given with the spatial resolution of of your kernel or the filter. How many number of channel is there in the filter? Many times it is not given also. And if it is not, why it is not given many times? Because it is by default understood that the number of channel in the filter will be exactly same as the number of channel in the input on which that filter is going to be applied. Right now, this 5 cross 5 filter I am going to apply on an input feature map having 96 channels. It means that this filter will also be created in such a way that it will have 96 channels. That's why this filter dimension is 5 cross 5 cross 96. So spatial size is 5 cross 5, but 96 channels. And if I'm going to again, now I'm going to repeat the same process again. 5 cross 5 cross 96. This is a channel. Just keep at a particular location and just perform the dot product for considering all the channels together. Then I will get a single value as the output. And the same process, repeat it by sliding it over entire spatial resolution of my input. Then I will get a channel in the output. Now this is going to be a deeper activation map, a channel in the output. Spatial resolution, because this is a 5 cross 5 filter. So 2 rows, 2 from each side we cannot cover right now without padding. And right now we do not have padding. So that we need to leave. That's why the dimension is decreased by 4, 2 from each side. So now the spatial resolution has become 24 cross 24. This is by using one filter of dimension 5 cross 5 cross 96. But now, as we have already discussed, only having one filter might not be sufficient. We need to consider more number of filters. For example, suppose in this case, if I consider 128 such filters, then in the output, I will have 128 channels. It means now what is the output dimension? 24 cross 24 cross 128. Okay. So now again, a very important thing. How many number of parameters are there in this layer? So in this layer, if I have to compute how many number of parameters in this layer, then what I will do, how many number of parameters are present in one filter multiplied with the number of filters. So how many number of parameters is present in one filter? That is how many number of values we have in that filter plus one bias term. So the number of values in that filter is 5 into 5 into 96. That many number of values I have plus one. That is bias for that filter. And that value, whatever we get, multiplied with 128, that many number of parameters we will have in this particular layer here. Similarly, even we can apply another level of convolution as well. So for example, this was 24 cross 24. Now if I apply, I can apply one more convolution, one more convolution, one more convolution, like that we can apply. So when we apply this multiple convolutions like this, then we get the deeper convolutional neural network. That's why that's what is called the deep convolutional neural network. Suppose if I have 20 number of convolution layers, 50 number of convolution layers, then it will become a deep convolutional neural network. But if I have only two number of convolution layer, or only three number of convolution layer, or only one number of convolution layer, then that is also convolutional neural network. But that is shallow convolutional neural network. But if you have more number of convolution layers, then that is a deep convolutional layer, deep convolutional neural network. Very important thing. Now, if you see, we already discussed the concept of local connectivity and weight sharing. So here we can see, I have a filter. That filter has some parameter. If I slide over that filter over entire image, then I will get one channel as the output. And in order to get every output, in order to get all the values in one channel in the output, we use exactly same filter. It means exactly same parameters are going to be utilized, because exactly same filter we are sliding over the entire image. We are not changing that parameter of that particular filter, which is giving one channel as the output. It means what? It means this is a weight sharing. This is weight sharing. It means same weights are going to be slided over the entire image in order to get all the output values in a particular filter. And also, if I'm getting one output here, then this one output is not computed based on all the input values. Rather, it is only computed from a 5 cross 5 spatial resolution of the input image. It means I have only taken a region of the input image of 5 cross 5, and for that also the center is exactly at the same coordinate where my output is there. If my output is there at 10, 10, then this my filter is also overlapped with my image by having center at 10, 10. And around that center, I have taken this 5 cross 5, this region from the input image across all the channels and perform the dot product. That is actually local connectivity, because what we have seen in the local connectivity, output neuron is not connected with all the neurons in the input. If I consider all the values in my input as the neuron, for example, just to correlate with the things, and all the output here as the neuron, then this output is only connected with 25 in each channel, is 75 number of neurons from my input. So it means that this is the local connectivity. And also weight sharing, because exactly same weights are going to be slided over the entire image. These two are the very important concept, and that has actually led to this neural network practically to work. And also, there are two more important characteristics with any convolution layer. One characteristic is handling multiple input channels. So even either you have one channel or two channel or 10 channel or 100 channel or 1000 channel in your input, it doesn't matter. You can handle it. Why you can handle it? Because if you have suppose 100 number of channel in your input, then your filter will also have 100 number of channels, and you can perform the convolution there. You can perform the convolution operation. That's what is one of the flexibility which is going to be provided by this convolution layer. And also, Any number of output maps we can produce, any number of output channel in the output maps we can produce. Suppose if I want to produce 10 number of output channels, what I need to do? I need to use 10 different filters. The number of output channel is always dependent upon how many number of filter we have. If someone has k number of filters, then k number of output channels will be produced in that particular layer. This is particular to a particular layer. Okay, so that also provides a flexibility that we can produce any number of output channels as per my requirement. Then a lot of customization flexibilities are given here. Okay, now let's come to spatial dimensions. So what will be the output dimension? Suppose if I want to compute based on if I know what is my input dimension, if I know what is my filter dimension, if I know what is my stride, if I know padding is will come shortly. If I know all these things, then what is the output dimension? A very simple formula will always give you. That is n minus f divided by stride plus 1. This is a very simple formula where n is the what is the spatial resolution of my input image or input feature, and what is f, what is my spatial resolution of my filter, what is stride, by how many number of positions we are shifting this filter. So for example, here suppose if n is 7, means if I have an image having dimension 7 cross 7, if I have a filter having dimension 3 cross 3, and in that case, if my stride is 1, then what will happen? If stride is 1, then this particular filter is right now here. I can shift it by one more position, one more position, one more position, one more position. How many times I can shift? One here, one is already there, then 2, 3, 4, 5. I can shift it by 5 times I can shift it. Then in output, I will get 5 values. So output dimension will be 5 cross 5. And the same thing I will get from the formula as well. 7 minus 3 divided by 1 plus 1, that comes to 5. But suppose if stride is 2, if stride is 2, right now one convolution will perform here, then shifted by 2 position, then center will come here. One more convolution we can perform it, shift by 2 more position, center will come here. One more convolution we can perform. It means the total number of convolution that we can perform here is 3. So, and that's what we get from the formula as well. 7 minus 3 divided by 2 plus 1 comes to 3. It means the spatial resolution of the output after applying this filter with stride 2 will become 3 cross 3. But suppose if someone wants to apply with stride 3, then right now we can compute it here. Now shift it by 3 position, then center will come here. We can compute again. Shift it again by 3 position, then center itself will go out of bound. And the last column we have not utilized at all. So it means that it will come into the fraction. So that's what comes here. 7 minus 3 divided by 3 plus 1 comes into 2.33. And that's what we need to avoid. Where it means whenever we are designing any convolutional neural network, we need to work with what is the input dimension, what filter we are choosing dimension, what stride we are choosing. These things we need to choose in such a way that this n minus f divided by stride plus 1, it should always come as the integer. It should not go into the fraction. If it goes into the fraction, that's not a good choice. It does not mean that it is incorrect. Still, it will work. The only thing, it will not utilize the last column. It will get redundant. It will be basically discarded. Our last column and last row will be simply discarded. It will not be utilized in future. But that's not a good way, because whatever input we have, we need to exploit everything. So that's why we need to always check that it comes as the integer. Okay. And also what we have seen, suppose if I have a 5 cross 5 filter, then what we have seen, this 32 cross 32, 32 cross 32 input image. When I apply 5 cross 5 filter, spatial resolution will become 28 cross 28. If I again apply 5 cross 5 filter, 24 cross 24. Suppose if I again apply, then it will become 20 cross 20. If I again apply, then it will become 16 cross 16. If I again apply, it will become 12 cross 12. If I again apply, then it will become 8 cross 8. If I again apply, then it will become 4 cross 4. And once it has become 4 cross 4, after that we cannot apply, because 4 cross 4 itself is smaller than filter dimension 5 cross 5. So it means that if I'm going to apply the filters like this, then I cannot build a very deep neural network, because once I have gone to this 8th or 9th layer, after that, the input dimension has been collapsed. When input dimension has been collapsed, we cannot utilize 5 plus 5 filter again. So that is basically one of the problem if we are not retaining the spatial resolution. So that it means if we are not retaining the spatial resolution, then we cannot build a very deep convolutional neural network. So that's where we have the concept of padding. And the concept of padding will ensure that every time when we apply the convolution layer, we retain the spatial resolution. Our spatial resolution should not get decreased like this every time. Okay, so what is padding? So usually we perform padding by zero. There are several ways of doing padding, but the common practice which is exploited in the deep learning for the padding is padding by zero. So what is meaning of padding? So now if I have the image size as 10 cross 7 cross 7, for example, then I will add one more row at the top also, on the bottom also, one more column at the left side also, right side also. Then this is called padding by one. This is padding by one. At every side, if I add a zero, that is padding by one. And if I do padding by one, then if 7 cross 7 input was there, so then its size will be changed to now 9 cross 9, because at every side one is added. Then overall impact it will make of 2. So this 7 cross 7 input is now actually changed to a 9 cross 9 input with padding. 7 cross 7 without padding, but now this is 9 cross 9 with padding. Okay, so now suppose if we again apply 3 cross 3 filter here, and if we apply 3 cross 3 filter, then how we can compute the output now? How we can compute the output resolution? What was the earlier formula? N minus f divided by stride plus 1. But in this formula, what we need to do, a small change we need to do. Instead of saying now n, now because n has changed now. Earlier n was 7, but now n is 9. Which basically effectively it is changed. So it means that if padding amount is P, for example, if padding amount is P, then it will get the impact of 2 times P in the height also, and 2 times P in the width also. So it means that if originally, if the dimension was n cross n, so after padding by P, now dimension will be n plus 2P times n plus 2P. So it means that in the formula, when we had n minus f divided by stride plus 1, now that n we need to replace with n plus 2 times padding. So now our revised formula would be n plus 2 times padding minus f divided by stride plus 1. That's what we need to understand. And here in this case, n plus 2p, n was 7, and padding by 1. So n plus 2p will become 9. So basically this 9, and 9 minus f, f is 3 here, which is a filter dimension. So which is 6 divided by stride. Suppose if my stride is 1, then plus 1. That's what will be the output dimension. And what we will see, 9 minus 3 divided by 1 plus 1 will give us the 7. So it means output dimension is 7. What was the actual input dimension? 7 cross 7. And if I have performed padding by 1 and then applied 3 cross 3 filter with a stride 1, then what is the output dimension? Exactly same as 7 cross 7. And we can also figure out, based on what is my filter size, I can figure out that what should be the padding amount such that after convolution, output dimension remains same. That we can always figure out. Suppose if my filter size is 3 cross 3, then we have to always do padding by 1. If my filter size is 5, we have to always do padding by 2. If my filter size is 7, we have to do always padding by 3. It's very simple. F minus 1 divided by 2. That is the padding amount that we'll always get. Okay. So now, in a summary, for a convolutional neural network, suppose if I receives an input of having dimension W1 into H1 into D1, where W1 is the width, H1 is the height, and D1 is the number of channels in my input. And if I have a filter, and that filter dimension is F cross F, because its spatial extent is written as F, it means filter dimension is F cross F, and number of filter is K, and the stride is S, means by what amount we are going to slide over, and amount of zero padding is P. Suppose if all these information is given to us, can we find out what will be the output dimension? W2 cross H2 cross D2 means width, height, and number of channel in the output dimension. Can we find out? Yes, that is very easy. If you want to find out W2, so what was the original dimension? What was the original width? W1. If we have the padding, then add 2 times padding in that. So W1 plus 2 times padding means W1 plus 2P minus what is the dimension of the filter F. So W minus 2P, W1 plus 2P minus F, or in other words, it is written as W1 minus F plus 2P. That is exactly same thing, divided by stride, which is S plus 1. That is going to be W2. Similarly, we can get H2. H2 is equals to H1 plus 2 times padding minus filter dimension F divided by stride S plus 1. That's how we can get H2. What about D2? D2 is number of channels in the output. And we have seen in the convolution layer, every filter will produce one channel. So how many number of channels we will have in the output, that will be directly dependent upon how many number of filters we had, and how many number of filters we had K. It means K number of channels will be there in the output, that D2 is equals to K. That's what. Okay, can we also compute the number of parameters? Yes, we can also compute the number of parameters. How to compute the number of parameters? Number of parameter in one filter multiplied with the number of filters. So how we can compute number of parameter in one filter? What is the size of the filter? Size of the filter is F cross F. Size of the filter is F cross F. But how many number of channels are there in the filter? Now, if you see in this entire input, in this entire thing, we have never written how many number of channels are there in the filter. What we are saying, filter dimension is F cross F, number of filter is K, but we never mention number of channels in the filter, because by default, number of channel in the filter is exactly same as the number of channel in its input. And input is size is W1 cross H1 cross D1, which actually has D1 number of channels. It means how many number of channels filter will have? Filter is also bound to have D1 number of channels. If filter has D1 number of channels and filter dimension is F cross F, then how many number of values we have in the filter? F into D1. That many number of values in the filter plus one bias term. So F into D1, that is the number of weights, multiplied with the number of filter, which is K. If we multiply it with the K, that is total number of parameters that we got, plus for every filter we have one bias, so K number of bias. So F into D1 into K plus K, that is going to be the total number of parameters in any convolution layer. Okay, so now there are some questions we can take, then we will move forward to another layer. Okay, so there is a question. Could you please explain one more time the significance of a channel in input or output? Okay, basically channel will have one type of, usually a channel will have one type of information in feature. In input, channel is having red channel, green channel, and blue channel, original input. But in any intermediate, if you are performing convolution layer, then the channels that you have in the input channels will have the feature or the information in a detailed way. It means detailed information in different channels will be there in the input, and in the output you will have the abstract information in different channels. Means the information in the channel is going to be utilized to transform them into more abstract information or more problem specific information. That's why if you slowly move from left to right, then your detailed information will get combined slowly, and at the end you will have very problem specific or abstract level information, which can be directly given as the input to your classifier. Okay. Another question is, in fifth shifting, one column will go out of, yes, that we need to avoid. That's why we need to pick the numbers in such a way that output dimension should be always in, it should not be in fraction. Another question is, in general, is there any selection criteria of filter and parameter selection criteria? Filter and parameter both are the same. There's no different. Actually, parameters are inside the filter. What we are saying, suppose if my filter is 5 cross 3, then these 75 values that I have my filter, those are only the parameters. So is there any selection criteria? So there is no selection criteria of the parameters. Parameters will be randomly initialized and training will happen, and it will be updated throughout the training process. What we can select is how many number of filters and what is the filter size that we need to select. Is there any criteria? Once you will do the study over this convolutional neural network, different models, then slowly you will understand that if you use a different type of filters, different size of the filters, then what is the impact? Then you will be able to have the intuition. So usually smaller filters is better, but more number of filters, more number of layers. That's what we basically want to have. So what does this zero padding mean? Zero padding is only used to increase the input dimension temporarily, such that output dimension will remain same as the original input dimension, only to retain it, only to retain the dimensionality. So another question is, I could only join the class 15 minutes back. No problem, you can watch again later on. So another question is, so each filter should have D1 number of channels. Yes, exactly. Each filter will have exactly D1 number of channels. Another question is, if the images under consideration are large in size, to what size should one resize them? Is there a rule for this? There is no such rule. That completely depends upon what is your computational resources that you have, how much you can afford. So suppose if you are having a good GPU, even you can do the experiment at 512 cross 512 resolution as well. But if you are having a smaller this level computation resources, then you can even resize to 32 cross 32. Batch size also matters there. You can also play with the batch size. If you have a good resources, you can have higher batch size. If you have low level resources, you can work with smaller batch sizes. Another question is, what is the functionality or philosophy purpose that this whole mechanism of filters and CNN provides? How essentially different from simple input matrix? Okay, that I will come to that. So there is another diagram that I have for this. So just you hold your question, you will get your answer. How to decide a padding so that it does not affect our feature extraction? Just zero padding. So simply use zero padding. And if your filter dimension is f, then f minus 1 divided by 2 should be the number of this padding amount. Another question is, I input here always have to be an image. Your input is image only for the first convolution layer. But suppose if you are applying the second convolution layer, so before second convolution layer, whatever layer was sitting, output of that layer will serve as the input to the second input layer. Similarly, if you are applying second convolution layer, suppose if you are applying the 10th convolution layer, then just before 10th convolution layer, whatever layer is there, for example, you have Renu or you have the pooling layer. So output of that layer will be input for that layer, that convolution layer. Another question is, why are we changing the number of filters? Can we use the same number of filters like 96 for all? You can use 96 for all, but what is the basic concept here? Even if you remember in neural network class, what we discussed there, in order to beat with this non-linearity, we can go with the higher order projection. So what happens here? Initially, we had 3 number of channels in my input image. Now we projected into 96 channels in one level. Then we further can project at higher level, like 128. We can further project at higher level. If we project at higher levels, then there is a high chance that we can convert my non-linearly separable data into the linear ones in final feature space. So that's why we usually increase it up to some extent, but later we have to decrease. Why later we have to decrease? Because at the end we have to converge to the number of class scores for all classes. So suppose if I have 10 classes, then at the end I have to converge to only 10. So that's why initially we can increase, but later on we have to decrease it. Another question is, what is the advantage of using CNN rather than image processing techniques? If we are taking features from image processing, we need CNN or a simple neural network is enough. We already discussed this. Maybe you missed that point. So if we are using simple image processing, then the performance of either CNN or neural network, whatever we are applying on the features extracted from image processing, that is actually suffered because if the feature that you have extracted itself is not having the required information from your input image required to solve that problem, then your CNN and neural network will be useless. They cannot do anything. So that is very, very important thing. That's why if you are applying the CNN, directly apply on the raw data. So that is going to be better because then CNN will automatically identify which feature is important, and then its filters will be trained in such a way that it will extract that sort of features automatically. Another question is, if video images are taken when one 7x7 is followed by another 7x7, should we consider 14x14 or padding as 9x9 and again 9x9? Your question is not clear. If video images are taken means, are you talking about multiple images or what? When one 7x7 is followed by another 7x7, should we consider 14x14 or padding as 9x9? Okay, you may elaborate your question again, then I will try to answer. Okay, now let's move forward. We have another type of layers also that quickly we need to discuss. Suppose another important layer is the pooling layer. So what happens here? Now we have seen whenever we are applying the convolution layer, we will perform the sufficient padding to retain the spatial resolution. But if we retain the spatial resolution throughout the network, then computationally it will become very complex, because initially number of channel is less, then we can afford higher resolution. But when number of channel increases, then and also if spatial resolution is also very high, then it will be again it will become computationally problematic. And in fact, here you can see. So for example, in this case, what happens here, now we are using 128 filters. Suppose next we are going to use 256 filters. And if we retain is the same spatial resolution, then what will be the computation load that we can assume? So that's where in convolutional neural network, it is also required that after some intervals, we should be decreasing the spatial resolution. And that decreasing of the spatial resolution is usually done using the pooling layers. And what pooling layer does pooling layer works on each channels independently. So for example, I take one channel from here and perform the downsampling and then place at the same order. Fine. So each channel independently and simply performing the downsampling. That's what is the task of this pooling layer. Now, how to perform this downsampling? For that, we can have several approaches. And one approach which is very common is the max pooling. So in max pooling, what we do, we take a local window and then just retain the maximum of that and throw out the remaining one. So for example, suppose if I have a max pooling with 2x2 filter, it's also called filter, but there is no parameters here. And a stride is 2. It means I will take a 2x2 window, retain its maximum and place that in the output. For example, this 1156 2x2 window, maximum is 6, 6 is placed in the output, and 511 will be thrown out. That's not required. And then because stride is 2, so shift this window by 2 positions. So if I shift this window by 2 position, the next 2x2 window is 2, 4, 7, 8. Retain the maximum one as the 8 and throw out others. Similarly, in this case, retain the maximum one as 3 and throw out others. Retain the maximum one as 4 and throw out the others. Okay, this is not the only way we can perform. There could be multiple ways we can perform. This is just one example that I am showing here. But very important thing to understand here, what is the significance of this max pooling? First of all, why this max pooling can work? Because we are removing some information. Are we not losing the sufficient information? So what happens here? Usually, the max pooling or any pooling layer, usually we apply after convolution layer. We have the convolution layer, we will apply some non-linearity on top of that, and then we apply the pooling layer. And now if you again recall, in convolution layer, we have a filter and we are sliding that filter over entire spatial resolution and we are getting a channel as the output. What was the characteristic of the convolution layer? That a filter will also have some characteristic. Means a filter have the characteristic that what sort of information it wants to extract from the input channels. And if that type of information is present anywhere in the input image, then it will give the higher output. Otherwise, it will give you the output values will be smaller. Means in the output channel, if we are getting somewhere the output at higher side, it means that at that particular location in my input, what sort of information my filter wanted to extract, similar information was present there because we are doing dot product. Now, if you see, whenever we do the dot product, if we are getting higher output, it means that both the vectors or both the matrices in between which we are doing the dot product, if they are aligned with each other, then only we will get higher output. But if they are perpendicular to each other, our output will be 0. And if they are not aligned with each other, output will be close to 0. So that's what is happening here. In max pooling, if we are retaining the maximum information, it means that what my filter wanted to extract, that information I am still retaining. It means most useful information I am still retaining. What I am discarding is actually the information which is not very much aligned with my filter. What my filter wanted to extract, if it is not very much aligned, those informations I am basically getting rid of, removing. So that's why, in spite of losing some information, still this concept is going to work because most relevant information is going to be retained. Okay, even someone can perform the average pooling. So for suppose instead of max pooling, if I want to perform average pooling, then what I will do, I will take the average of this 1156, place it here. Then average of 2478, place it here. Average of 3212, place it here. Average of 1034, place it here. So that's how even I can perform the average pooling as well. So this depends upon us which pooling techniques we are utilizing. So usually if we are using this max pooling towards a start or middle, usually we perform max pooling. But something if we are doing towards end, suppose if I want to apply these pooling layers towards inside, then usually we go towards the average pooling, because towards inside we don't want to lose the information, because your information is already in an abstract way. So we don't want to get rid of most of the information. So that's where you add towards inside, it is preferred to have the average pooling, but towards early layer or middle, max pooling is okay. Okay. So again, what will be the dimensionality, output dimensionality of the max pooling? That also we can compute. Suppose if the input dimension on which we are applying max pooling is W1 cross H1 cross D1, and if my pooling layer has filter size F cross F and stride is S, then output dimension we can simply compute W1 minus F divided by S plus 1 in very similar way like we have seen in convolution layer. Similarly, H1 minus F divided by stride plus 1. Number of channel D2. Okay, here is a difference. In convolution layer, number of channel in the output was dependent upon number of filter. But here we do not have number of filter. We have only one filter, which is just the pooling layer. Just the what is the what is going to be the size of the window in which we consider the pooling layer. That's what is the spatial extent. This is the only information we need to provide here. And because this happens on each channel independently, so the number of channel in the output will remain same as the number of channel it was in the input. So that's why D2 is equals to D1 is mentioned here. And also, if we talk about number of parameters, because there is no parameter, we do not have anything which is going to be learnable or something, because we do not have any parameter. So that's not going to be, means the number of parameters will be zero in this case. Other type of layers we have like fully connected layers. Fully connected layers we have already seen that is already there in artificial neural network, where every neuron receives the input from all the neurons of its input layer. And then why, if we have a convolutional neural network, so why fully connected layer is required? That is one of very important question. Why fully connected layer is required? So this question I will simply hold when I will show overall diagram of a convolutional neural network. At that time I will take this question, why a fully connected layer might be required even in the convolutional neural network. Okay, other important layer is non-linearity layer, which is also called the activation functions. This is one of the important layer that we have seen. We will have a quick look on this activation function. Sigmoid, you can see. So sigmoid looks like this. That is 1 divided by 1 to e to the power minus x. Sigmoid converts everything between 0 and 1. But the problem with the sigmoid is, if you see for most of the negative inputs, this is a flat surface. It means its gradient is 0. For most of the positive inputs, also, this is a flat surface. It means its gradient is 0. And we have already seen in optimization, gradient is very, very important thing. And if your gradient is going to be, local gradient is going to be converted into 0, it will actually influence the downstream gradient. That is also going to basically a running gradient that will also get influenced, that will also become near to 0. And when gradient is compromised, that gradient diminishing problem will come and entire optimization will be suffered. And that's what happens with the sigmoid. Another problem with the sigmoid is it is not zero centric, and we want most of the time we want values to have positive also and negative also. Means some positive values should be also there, some negative values should be also there. That is also from the optimization perspective. Whatever input we have, or whatever input feature we have, if we do not have both positive and negative values, then optimization becomes very difficult. And this is again another, there is a reason for that, and the reason is related to the optimization itself. That's what is the reason. Even if you see in case of convolutional neural network, most of the time we show that we perform the data normalization before feeding the data to the convolutional neural network, because we convert because images are always positive, pixel values are always positive, but we convert those pixel values in negative also by performing the normalization, so that roughly half of the values should be positive, roughly half of the values should be negative, so that optimization will be not problematic. There is a tanh. Tanh is also like sigmoid only, but instead of squeezing in between 0 and 1, it is squeezing between -1 and 1. So one problem that sigmoid output is always positive is resolved in tanh, but still there is a problem that gradient diminishing problem, because for most of the negative inputs and positive inputs, its gradient is roughly 0. There is a ReLU that is called rectified linear unit, and this is most commonly used in deep learning, this ReLU activation function. And why this is commonly used? Because if you see, for all the positive inputs, its output is exactly same, and we have some good amount of gradient as well. And in fact, that gradient is exactly 1. It means whatever gradient we are getting from the output is going to be multiplied by 1 and passed as it is as the input. But it has a problem. What is the problem with the ReLU? For all the negative values, it converts into 0, and gradient is exactly 0. It means if you are having the negative inputs, then gradient diminishing problem will come. And in general, for ReLU, it is called dying ReLU problem. Because if you have a convolutional neural network, you are using the ReLU activation function, then this ReLU activation function will eventually make half of the neurons of your neural network to be dead. Why it is dead? Because gradient, there is a 0 gradient for those neurons. Those neurons are never activated. They are completely dead. So half of the neurons are usually dead if you are using the ReLU activation function. Then how this problem can be resolved? So this problem can be resolved by having some other variations of the ReLU, or just have the data distribution to be followed Gaussian, and that to be enforced manually. So it means batch normalization becomes compulsory. If we use batch normalization with ReLU activation functions in the convolutional neural network and neural network, then the effect of the ReLU will be, means this particular problem will be compromised there, and then ReLU is going to work better. So most of the time, whenever ReLU activation function is used, batch normalization becomes one of the compulsory things to be utilized, because batch normalization will remove the negative impact of the ReLU by simply converting this feature distribution itself to such that it should follow the Gaussian. Okay, other ways of improving the ReLU is to make sure that these input values are also going to be exploited, like leaky ReLU. In case of the leaky ReLU, a small fraction of the input values are exploited. So now we will not have the 0. We will not have the gradient 0. So leaky ReLU, but leaky ReLU sometimes it works better, sometimes it doesn't work better. There is no concrete evidence that it is always better. However, in this particular, there is a lot of work that people have done in this particular area, like max out. So max out basically doubles the number of neurons, and then it repeats the process 2 times and takes the maximum of that. So that is a max out. ELU also tries to try to improve this ReLU by considering the negative values. And negative values are considered using this exponential function. This is alpha into e to the power x minus 1 here. So this ELU can be also utilized in the practice. However, if we are using ELU, then computational load will increase because we have to use exponential function. And one of the important thing why ReLU is preferred in practice, because it is very fast. Because we do not use any exponential function, any logarithmic function, nothing is used. All positive values passed as it is, all negative values converted to 0. So this is going to be very fast. That's why this is very well exploited in the deep learning. Impact of the neurons we already discussed last time also. If we have more neurons, then basically our model will be able to learn the decision boundary even for very complex data as well. So this is the sigmoid activation function that we already talked here. For the sigmoid activation function, which is related to the firing rate of the neuron, means 0, not firing, 1 fully firing. So output is in between 0 and 1. But the problem is gradients at these regions almost 0, almost no signal will fall, means gradient diminishing problem will come. It will kill the gradient that we have seen. tanh will resolve one of the problem of the sigmoid, means it is zero-centric, but still it is again having the problem of gradient diminishing problem. ReLU, we have just seen, it is much faster, accelerates the convergence of SDD optimization due to the linear non-saturating form, and less expensive because we do not use any sophisticated exponential or logarithmic functions compared to sigmoid and tanh. In practice, it is six times faster than sigmoid. more expressive and prevents the gradient vanishing problem for the positive inputs, but for negative inputs, it is still there. Okay, and one important activation function in practice, it works very well and very recently proposed in 2018, and that is called the Swiss activation function. And this Swiss activation function tries to control the amount of non-linearity required for a particular problem. So what it tries to do, it tries to control the amount of non-linearity between linear function and ReLU activation function. So what is this activation function? This is x into sigmoid beta times x, where beta is one of the hyperparameter, and this beta actually controls. Beta is the parameter that can be even learned using the network. So automatically, if we learn this beta from the network itself, then automatically it can control the amount of non-linearity. How it can control? So what happens when this beta is smaller, like 0.1? Then this Swiss activation function behaves very similar to the linear function. It means that suppose if you are having a problem that you are solving, and that problem is already linearly separable, for example, then non-linearity is not required. When non-linear, but still if you are using the activation functions like Swiss, then in that particular case, what will happen? This Swiss will automatically learn this beta to be smaller such that this amount of non-linearity is roughly negligible in this case. However, if you are solving a complex problem where more non-linearity is required, then this beta will be automatically learned to the higher values, like 10 here. And when beta is like 10, then this particular function will behave very similar to the ReLU activation function. So that's why this is going to be one of the important activation function that it can control. It can control the amount of non-linearity, and at the same time, it does not suffer with that gradient diminishing problem by controlling this beta values. So that is going to be important thing here. So sometimes we need to also utilize the regularization into this convolutional neural network, this regularization layers. And important regularization layers, two important regularization layers are dropout and batch normalization. And in dropout, what we do, in dropout, we randomly drop some of the neurons from each layer. And how many number of neurons to be dropped, that is controlled by some probability. And that probability we need to provide. Suppose if you are saying that apply this dropout with the probability 0.5, then 50% of the neurons will be dropped. They will not be considered in that particular in that particular iteration of the training. Similarly, then what is the advantage of that? So for example, suppose if overfitting is happening, for example, we have a neuron, and let's assume that we wanted to learn this cat characteristic and wanted to classify this one as the cat, given input image as the cat. And suppose there was a neuron, and that neuron was overfitting a particular characteristic of the cat. Means whenever it sees the furry, then it was being activated. So it means that when it is dependent on a particular characteristic, then that is overfitting. It means a single neuron should not be responsible for a particular characteristic. It should get distributed. If it is not distributed, then overfitting is there, then regularization is required. So what happens when we apply the dropout? Suppose this particular neuron was responsible to that particular characteristic, and when during training in a particular iteration, that particular neuron itself is dropped. When it is dropped, then representation of that feature, which was also very important to take the decision, is now missing in the final feature because that neuron is not part of the present iteration. So, and only that neuron was extracting this in particular information, so that information is missing now. Then what will happen? If that information is missing and that was very important to take the decision, then loss will increase because misclassification will happen due to that. And if loss will increase, then our neural network will think that, okay, if loss is happening, it means something goes wrong. It means we need to better look the characteristic of the input. Then slowly it will figure out that the characteristic that was important, that characteristic is not present in the final representation. Why it is not present? Because the neuron that was responsible to extract that characteristic itself is dropped. It is not present in that particular iteration. Then what neural network will try to do? It will try to activate some other neuron to learn that particular characteristic. And but maybe in the next iteration, the next neuron, other neuron which is going to extract it is also dropped. Then again there is a problem. Then slowly what will happen, our neural network will figure out that a particular information should get distributed across multiple neurons, such that even if some of the neurons out of that is dropped, still the contribution of that characteristic must be present in the final representation. And that's how it actually increases the regularization. And if it increases the regularization, then it can work well on the unseen data. Similarly, we can use a batch normalization also. What batch normalization does, we get the output, we get an activation map, and then we compute this mean and standard deviation of the activation maps and on the batch wise data. And if we compute that, then mean is subtracted here from the feature values and divided by the standard. Basically, it's normalization. Because it is computed on a batch of data, batch wise, that's why it's called batch normalization. So, and what this will do, what impact it will make when our feature, where our feature distribution was getting disturbed due to different layers, then it is going to be again controlled to follow the Gaussian, and which is going to be better in terms of the regularization. Obviously, at the end, we need to utilize different losses. So what loss we have seen. So what problem you are solving, we can have a different objective function. We can have a different loss function. Suppose if we are doing image classification, then we can have the softmax loss and cross entropy loss, or cross entropy loss in softmax classifier. If someone is solving a problem of finding a bounding box of the face, then we can have the regression loss of the bounding box there. So based on the problem, what we are solving, we can have a different loss. We have already discussed what is the softmax loss. There is SVM classifier can be also utilized. I'm not going to that. If you are familiar with the machine learning basic concept, then you can correlate it. Okay. So now if you see here, if we just combine everything, then we will get a complete convolutional neural network pipeline where we have the input image, and that input image is passed to the convolution layer. Convolution layer will extract the features. Then it will be passed to the non-linearity layer. Non-linearity layer will introduce the non-linearity, means non-linear feature projection. And after that, we have the spatial pooling. Spatial pooling will ensure that important information is retained, other information is extracted, because slowly we have to decrease the dimensionality. And then basically we get this feature map. And this process we have to repeat multiple times in any convolutional neural network. So for example, here we can see. So we have the input image, then there is a convolution layer, pooling layer. Again, we have convolution layer, pooling layer. So now you might be seeing that we have convolution layer, we have pooling layer, but where is the activation function? So most of the time when activation function is not shown separately, then by default, it is followed by the convolution layer. It means if it is not shown here, then convolution layer, activation function, then pooling layer. Convolution layer, activation function, pooling layer. Fully connected layer, activation function. Fully connected layer, activation function, or softmax function we can have on top of that. So now this type of, and in between we can have somewhere a dropout layer also, somewhere we can have the batch normalization layer also. At multiple places we can place those dropout and batch normalization layers as well. So now let's again come to that question. If we have a convolutional neural network, then why we need the fully connected layer? And also, in any convolutional neural network, if we have fully connected layer, then those fully connected layers are only towards end. We cannot have the fully connected layers towards starting and then convolution layers at end. No. Because initially we are retaining the spatial resolution, spatial structure. And once we are reaching towards end, then at least one fully connected layer is compulsory. Why it is compulsory? Because at the end we need to produce the output. How many number of outputs we need to produce, based on that many number of neurons is required there. So if suppose if I, for example, here in this case, if I have 4 classes, dog, cat, boat, bird, then we will have the 4 neurons here, and 4 neurons will produce 4 class scores for these 4 classes. And on top of that, we will have the softmax classifier, which will convert these class scores into the probability. And in fact, where we are seeing here is actually converting into the probability. So this is the output of the softmax. On top of that, during training, we can have the cross entropy loss, means negative log likelihood of the probability of the correct class that we can compute and perform the training. But sometimes you will find in convolutional neural network that at the end, not one, but even we have 2 or 3 or 4 number of fully connected layers. So one is compulsory, but it is not compulsory to have 3 fully connected layers. Even we can manage with one also. So when we can have more than one fully connected layers at the end, that is dependent upon how deep convolutional neural network we have. Suppose if you have a very deep convolutional neural network, suppose if you already have 50 convolution layers, then you do not require to have more fully connected layers at the end. So then only one fully connected layers just to have the final prediction is sufficient. Why? Because if your input image has been processed through 50 number of layers, then the final feature that you have is already very abstract features. Then we need not to have the fully connected layers on top of that. But if you have a shallow neural network, a shallow convolution neural network, suppose you have only 2 convolution layer, for example, suppose we have only 2 convolution layer, then what happens? Suppose at the end of the second convolution layer, if I'm getting some output, that output doesn't see the entire image. Rather, it is only seeing some local region of the input image. Based on that local region of the input image, that feature is derived. So it doesn't have the global view, and that's not good. It means that it doesn't have the abstract view of the entire image. And because though convolutional neural network is processing the based on the local concept, but when we are having the final feature which is given as the input to our softmax, there we will have the global relationship should be also encoded there. Then only we will have the final abstract level feature representation of my entire image. So that's where if we have a shallow convolutional neural network, means if my number of convolution layer is less, then we must have the more fully connected layers. Because if we have more fully connected layers, then in that case, what will happen? And we know that in fully connected layers and a neuron in the output layer is receiving the inputs from all the inputs. It means that every input will be considered here for every neuron in the fully connected layers. Then obviously, a particular feature in this layer might be seeing only a portion of the image, but if I consider all the output, then someone might be considering this. Someone might be based on this particular reason, other might be based on this reason, other might be based on this reason. If I take the union of all these regions, then eventually it will cover entire image. And because everything is going to be considered as input in the fully connected layer here, then actually it is going to have the global relationship encoded here. So in a very quick summary, when to use more fully connected layers if we have a shallow convolutional neural network, when to use only one fully connected layer if we have a very deep convolutional neural network. So now there is an ImageNet. ImageNet was one of the challenge which basically had larger scale data sets, means a lot of images are there and they launched a challenge. And this was one of the important thing. Why this deep learning, even in image, in computer vision, we are able to work because there was GPU-based processing and large scale data set was available. And there was on this progress here in 2012, the first CNN model came, which was success. Actually, first CNN model came in 1998 itself by Jan LeCun, and he was utilized on that was called LeNet that he used for the digit classification. But after that, there was no much progress because there was lack of computational resources. GPU-based computation was not there much. Data set was very small scale, so that's why there was no much success. But in 2012, when this deep learning started, then this first model came, AlexNet, which became very popular and with 16.4% error rate. And after that, a lot of modifications came in this convolutional neural network. And now this is another, maybe in some other session, it is going to be discussed, these different variants of the convolutional neural network that might be discussed in some other session. So that's all for this particular session. Now, if there are questions, let's take those questions here. Okay, so what question is, what is the advantage of using CNN rather than image processing techniques? I think we have already answered this question. Video image are taken. Okay, so he has again written frame 1 7 cross 7, frame 2 7 cross 7 after padding frame 1 9 cross 9 and frame 2 9 cross 9 as separate images? Yes, padding will be performed on every channel, exactly. So suppose if you are having 3 channels, suppose if your original size was 7 cross 7 cross 3, then after padding it will be 9 cross 9 cross 3, means in every channel padding will happen. Another question is softmax also treated as an activation function? Softmax we can treat as an activation function if we apply that softmax somewhere in between, but that's not a very good concept. However, softmax is applied in between in nowadays in transformers because their purpose is different. Their purpose is attention mechanism, because softmax is giving us the probability, so that probability can be utilized to and it can be related to the attention. That's where it will work properly. So, but if you want, you can utilize even in between also as an activation function. There is no harm of that. Another question is convolutional neural networks apply weight sharing and local connectivity, which gives lightweight models. But still, if we go to FPGA deployment or any other hardware deployment of a DL model, it is said that still it takes much more computations and more consumption. Yes, very good, very nice. Yes, because still, even after doing all these things, still the model we have used number of parameters, we have used computation. So that's where the definition of lightweight convolutional neural network comes, where whatever model we have, we do the further pruning of that. We further find out for any given problem, what are the filters which are redundant, we identify that, we remove that. So just by doing all these things, we will be able to get a pruned and lightweight version of that convolutional neural network, which can be suitable for this resource constraint devices. For example, like this NVIDIA Jetson board. We have already tested on NVIDIA Jetson board for face recognition problem. One question regarding filters. So when in one layer we are applying 96 filters, so my all 96 filters have to be same dimensions. Example 5 cross 5 cross 3, or can we use different dimensions like this. So if you are using a plain convolution layer, it should be of exactly same dimension. If you want to have a different dimension, then you have to use like inception net. So in inception net, in the same layer, different dimensions are used, but it is applied independently, and then output is basically concatenated. So that you can get to know when you will study the inception net, Google net concept. Another question is, how can we apply the CNN concept in video, like how dimensions of the layers will change if we include frame rates of video along with the image dimensions in the channel. We also have a time factor. Yes. So there are multiple ways we can deal with the videos. One way, we can use the 3D convolutional neural network, where our convolution will have one more dimension, and sliding will happen in height and width, and also sliding will happen in time. So means sliding will happen in three ways. So that is called the 3D convolution. So that's how we can utilize, or we can utilize in a recurrent neural network fashion. If you're already familiar with the recurrent neural network, then in recurrent neural network we process one image, and then whatever whatever feature representation we get, that will be utilized as another input when we process the this frame at the next time stamp. So in a recurrent neural network fashion also we can use. Another question is, in regularization, what is meant by retaining fixed probability? Would not probability change? Some units are dropped off. Probability we can change, it's up to us what probability we are keeping. So for some layer, suppose if you are using dropout, you can have 0.5 probability, someone can have 0.6 probability. But if your dropout probability is very high, you will suffer with your optimization, because then you are not having the sufficient information extracted from your input. Effectively your neural network will become very small. So that is also going to be a challenge. So that's where you need to balance. So usually dropout rate maximum, we usually go up to 0.5. It should be 0.5 or below that, like 0.5, 0.4, 3, 2, 1, like that. W minus F divided by 2, can you again explain how the formula came? W minus F. Okay, this is very simple formula. So suppose if W is the width of your input, F is the size of your kernel, then what will be the output dimension? So W minus F divided by, it is not divided by 2, it is divided by stride. So whatever it means by how many number of positions you are shifting your window. So this is W minus F. This is not F by 2. This is W minus F overall divided by stride. plus 1. That's what will be your output dimension without padding. If you have padding, then it is W plus 2P, means padding amount is P, then W plus 2P minus F overall divided by stride plus 1. Another question is, kindly explain batch normalization in simple terms. Batch normalization, what happens here? Suppose if you have the ReLU activation function, whatever your input, it doesn't matter, your output is always positive. There is no negative value in the output. All negative values are zero, converted to zero. And that is not good for optimization. So what happens? This batch normalization, if you apply this batch normalization, then it will make sure that this distribution is again going to be converted into zero mean unit standard deviation. So that distribution, when it is converted into zero mean unit standard deviation, then roughly half of the values will again become negative and half of the values will remain positive. So basically it will follow this type of distribution, which is going to be good thing for the this optimization perspective as well as generalization perspective. So that's why batch normalization is one of the very important layer in convolutional neural network, especially if you are using ReLU activation function. Another question is, we can apply lateral normalization and batch normalization, layer normalization and batch normalization, both are, we need to apply one technique only. At a time, you can apply only one technique, but in even in the same neural network, same convolutional neural network, maybe you have applied the batch normalization, then some more different layers, then again you can apply the layer normalization. It's again up to you. So you need to see that for that particular problem, this is going to work or not. Okay, so that's all the questions. So thank you very much. I think we also reached to end of the session and already some 5 minutes are delayed. So thank you very much for listening this particular session, and all the best for the remaining sessions in the course. So now we can stop here.
Thank you so much, sir, for another excellent session. It was truly informative and engaging, and we really appreciate your time. Thank you so much.